All right, so let's start. This is the first of our series of lectures on training neural networks. So here are all of the topics for the day. We're going to look at the problem of learning, the perceptron rule for perceptrons, and why we can't apply it to multi-layer perceptrons. We'll briefly touch upon greedy solutions for classification networks. I actually won't spend time on it. Most of it's going to be hidden slides. We'll look at learning through empirical risk minimization and an introduction to function optimization. This is the first of a series of lectures, so I don't expect to finish all of these topics in today's lecture. These will sort of flow kind of continuously over the next 5 lectures. Now, here's what we know so far. Neural networks are universal approximators. They can model any Boolean function, any classification function, or any real valued function, just so long as they have the minimal architecture needed for the particular function that you're trying to model. And so they can model all of these functions to perform very complicated tasks like transcribing speech or captioning images or suggesting the next move for a game. Now, in each case, what these functions are doing is to take some kind of an input like the voice signal or the image or the game state and computing an output like the transcription, text caption, or the next move. But consider the mechanics of it. This is a numerical machine. It works off numbers. It takes in numbers and outputs numbers. So this means we have to worry about 2 issues. How do we represent these inputs, the speech signal or the image or the game state, and how do you represent the output, the transcription or the caption or the prediction for the next game state? So these are 2 topics we do have to worry about. And then there's another equally important topic, which is how do we actually compose the network that performs all of these functions? Now, in today's lecture, we are just going to focus on the business of composing the network. Let's begin by looking at the basic units of our network. The perceptron. Here is the perceptron. It operates on real valued inputs. And first, it computes an affine combination of these inputs, which is to say a weighted sum of these inputs plus a bias. And then it applies an activation function on this affine combination. The basic activation that we've seen so far is the threshold activation, but in reality it can be any other kind of activation like the sigmoid or the ReLU or the soft plus. Now the parameters of this perceptron, which are the weights and the bias, determine how it behaves. Now instead of having, this is just a little aside, instead of having an explicit bias going into the affine combination, I can get exactly the same computation if I extend the input by an additional value, which is always 1. And now the weight corresponding to this new component is going to become the bias. The advantage of writing it this way is that I don't have to explicitly write the bias out here in the affine combination. I can just write it as a weighted sum of inputs and the whole thing still works. So often in my slides, yes, Sammy? Go ahead.
I wanted to ask, why are we assuming that the bias will be 1? Like, why can't we use a different number?
So the bias is not going to be 1. I'm augmenting the input by a value 1. The weight for this guy is going to be your bias. Make sense?
Okay.
Right?
Okay.
This is just for convenience. This is just for convenience, okay?
All right.
So in my slides, if I don't show you an explicit bias, it means I've done something like this. And and the entire network, of course, is just a network of perceptrons, and we are going to assume a feed-forward network, which means the computations are going to go strictly in one direction from the input to the output, left to right in our figure. This means that in processing any particular input, each neuron in the network is computed exactly once. The signal doesn't go out and come back through any kind of path to a neuron. These things are not loopy. We will consider loopy networks later in the course. So now a major part of designing such a network is the architecture of the network. How many layers do we have? How many neurons do we have in each layer? We discussed this in detail in the last class. For now, for the rest of the series, we are going to assume that we have somehow obtained the architecture, an architecture for the network that is capable of representing the needed function. So we're not going to worry about the architecture of the network. And so now when we think of it this way, each perceptron is a little function which operates on the input and computes its output. The network is a combination of such functions. So the network itself is just one giant function which takes an input x and produces an output y. And the parameters of the network are the weights and biases for all of these connections. So I can write the network as y equals f of x semicolon w. This is a standard notation. When we put a semicolon over here, it means the term before the semicolon is an argument to the function. The term after the semicolon represent the parameters of the function. And so the w's here are the parameters of the function. And now if you want them to make the network compute a specific function, if you want it to behave in a particular way, then what that means is that you really want to set these parameters, these w's, such that the function does the right thing. And so these are the basics here. This is what we're going to assume all of you understand. Questions? Anyone? No? Okay, let me move on. If you have any questions, now's the time to ask. It just keeps getting deeper and deeper. So here's what we have. The MLP we know is a universal approximator. It can represent any function at all to arbitrary precision, and even if I have some fixed architecture, it can approximate any function to a pretty fine degree. So which means that given any function at all, I can construct an MLP that computes it. The problem really is, how do we compute this, construct this network? Now, the one solution is, say, I'm going to construct it by hand. So let's say I want to construct an MLP to compute this diamond-shaped decision boundary over two-dimensional inputs. I can do this with a network that uses threshold activations. I'd first construct one perceptron to capture this boundary. Now I know this boundary is a line, and this has a slope, and if this has a slope of 1, so the equation is going to be either x1 minus x2 plus 1 equals 0, or the negation of this, which is minus x1 plus x2 minus 1 equals 0. I want this guy to be on the one side, so I can plug in 0, 0 into both of these equations, and I'll pick the equation where the output is positive. That's going to be the first guy. And so when x1 and x2 are both 0, this one is going to give you a value of plus 1. And now I can use this to construct my perceptron. The weight for x1 is 1, the weight for x2 is minus 1, my bias term is 1, and this perceptron will capture this boundary. I can use the same mechanism to capture each of the subsequent boundaries, and then finally add the whole lot to hand construct the MLP that computes this decision boundary. Now, what's the problem with this approach? Anybody want to tell me? Anyone?
Need to know the decision boundary beforehand, right?
Yeah, number one, I need to know the decision boundary beforehand. And secondly, except for the simplest problems, it's simply not possible to do something of this kind by hand, right? Handcrafting networks is a tedious and possibly impossible task. So it's back to the drawing board. Here's a better option. I know if I'm given a function g of x that I want to model, then I can somehow derive the parameters of the network that model it accurately. Again, I'm assuming that the architecture of the modulus of the network is given. So here's how I do this. What I'm given is, so assume that I have a one-dimensional input for now. So what I'm given is this function g of x, which could be anything. This is g of x. This is the function that I am trying to model, and the network at any point, if I set the parameters of the network to be anything at all, that network represents a function, and that function will be something else, say this guy. And so there is this error between what the function actually computes and what the function we want is. So what we can now do is to somehow quantify this error, which is this area in the figure, in this figure, and try to estimate the parameters of this network such that that error is minimized. Now, of course, in order to do this, we need to be able to sort of quantify this area. So what we will do over here is, first, we are going to, do I have a different color? Let's see. We're going to define some measure of the difference between the actual output of the network that you want and the current output of the network. This guy is what I will call a divergence. This divergence has a property that it will be 0 if g of x is exactly equal to f of x. It will be positive otherwise. So here is the criterion. It should be 0 if g equals f. It should be positive otherwise. And now this quantifies the error at every point. So this entire area is simply going to be the integral of this divergence between f and g computed over the entire input. And what we want to compute is the set of weights that minimizes this divergence. Makes sense to everyone? Raise your hands if this didn't make sense. Anyone? I'm going to continue building on this. Yes, Bayram?
I was wondering, why do we take the integral of it?
Right. Okay, so here is the function. This is what it is, right? Let's go back here. This is a function. So you understand that why we must minimize this area, correct?
Yes.
Okay. An area is an integral. It's a volume for entire
dimension.
dimension.
Of course, right.
Right. So this is basically what we want. If you want to minimize the error everywhere, it must be the integral. You have no other choice.
That makes sense. Thank you.
Right? So what is the problem with this approach? Trying to do this, trying to estimate W that minimizes this area. Anybody want to tell me what the problem is with this guy?
You may not have access to every single instance of X.
You don't know the function G everywhere. You just don't, right? In most real life problems, G is not fully specified. Whereas in order to be able to compute that, we need to specify G everywhere. So here is what we will do instead. Instead, what I will do is, again, let me see if I can get the colors. I like colors. I'm going to pick some arbitrary points X on my axis, x-axis. At each of these guys, so let me draw this function spooling, right? At each of these locations, I'm going to record what the actual value of the function I want to compute is. So I'm not computing, we wanted this at every X. Instead we're just computing it at we are sampling the function at a certain number of locations. Those dots represent the samples. And now, so these are what we will call our training samples. And we are going to, and now we will try to estimate the function such that the function actually, when you optimize the network actually, the function that it computes actually goes through these points, these dots. That's what we're actually going to try to minimize, try to achieve. Instead of computing the function everywhere, we would have sampled a collection of input output values, and then we are going to try to estimate these estimate the parameters of the network such that at these inputs the function actually goes through all of these guys. And the hope is that if I actually get this right, so now I'm just going to have these dots, and the hope is that if I actually get a function that goes through these dots, it's going to be correct everywhere. That's hope. The only guarantee you have is that you can measure, but it's actually gone through these points. Make sense to everybody?
Professor, a few students have questions about why the divergence should be positive and not negative, or is it 0 or something?
Okay, so why the divergence should always be positive is again obvious from this guy here, right? Over here, look at this figure. If the divergence is allowed to be both positive and negative, then a negative divergence over here, a negative divergence over here is going to cancel out a positive divergence over here. And so you can have two functions which are very different, but the average divergence can be 0. Does that make sense? Anyone? So if you have any doubts about that, raise your hands. Okay, so let me continue, right? Yeah, Tanya?
Yeah, sorry, I didn't get that at the last point you made about the divergence.
Okay, here it is, right again. So what am I doing when I compute this integral? I'm computing the average. Basically, I'm computing this area, right? Now this area is the integral of the divergence over the entire space. Now consider this plot here. If this black line is the actual function you want, and the red curve is the current estimate of the function by the network, then if you plot the divergence over here, the divergence here is negative because the function is underestimating until here. And so the divergence is something like that, correct? If I take the average of all of these divergence values, this guy is going to cancel out this one. This guy is going to cancel out this one. This guy is going to cancel out this one. So for this particular approximation, you're going to get the assumption that you're going to be told that the average divergence is very small. And if you just based it on the the area over there, the positive and the negatives will cancel each other, and you're going to get the assumption. You're going to end up with the assumption that the function currently estimated by the network is pretty good, which it is not.
Okay, thank you.
Are you sure you got that, right? Are you?
Yeah.
Okay. There was another question, Ria?
Professor, I had to ask, when we're sampling the X's, is it supposed to be random sampling or is it supposed to follow a distribution?
We will get to that.
Okay.
But basically, you want the data, the samples to follow the natural distribution of the data. And this is very easy, right? In real life, this is just a question of gathering data.
Okay. Thank you.
Yeah. So what we really have now is that we don't have the entire function, we just have these samples, and we have to estimate the function from these samples. And basically, what we are going to try to do is to estimate the function such that it fits these points, which we will now call the training points, exactly, because that's all the information we have. And this again is assuming the network architecture can actually do it. If you don't have sufficient architecture, even this will not be possible. And the hope here is that if you fit the function at these points, then the resulting function is correct even where you don't have points. So here's the story so far. Training a neural network is the same as determining the parameters of the network for it to model a desired function. Ideally, we would like to optimize the network to represent the desired function everywhere, but this requires knowledge of the function everywhere. So instead, we draw input-output training instances and estimate network parameters to fit this input-output relation at these instances. And this is just a hope. There is no guarantee. You hope that it fits the function everywhere else as well. So let's begin. Now, this is for any problem, but let's begin with a simple task, learning a classifier. Now, learning a classifier is simpler than learning regression. And in fact, this was amongst the earliest problems addressed using NLPs. Specifically, I'm going to look at binary classification because this generalizes to multi-class classification. Multi-class classification can simply be thought of as many binary classifiers. Now, we'll start with the original multi-layer perceptron as it was proposed by Minsky. It's just a network of threshold activation perceptrons. And we are familiar with the threshold activation perceptron. Now, the question is, I have an MLP, how do I learn it to model a specific classification function using only training instances of input-output pairs? Now, what is the simplest MLP? The simplest MLP is just a single perceptron. So let's start off by considering the simplest MLP, which has only one unit. This we know is basically a linear classifier which captures a linear decision boundary. The actual function itself is the step function, or what is called a heaviside function. It's 0 on one side of this boundary and 1 on the other side. And what we are trying to do is to try to learn the step function. Except we are not given the entire function. We are only given some input-output pairs like these blue and red dots, where the y value of blue will be 0 on one side, or the blue dots will be 0, and the y value of the red dots will be 0. And we must learn the function from only these pairs. You don't actually have the entire function. Now, the output of the perceptron is given by this by now familiar formula. It is 1 when the affine combination is positive and 0 otherwise. The actual boundary is a hyperplane. So learning the perceptron is the same as learning the equation for the hyperplane, such that all the red dots are on one side and all of the blue dots are on the other side. And now, just for convenience, I'm going to redraw the perceptron without this. The perceptron basically computes an affine combination, remember? I'm going to redraw it as a linear combination by extending the input by an extra 1, exactly as I showed earlier, because this is just for convenience. So now this means that if the linear combination of this extended input is positive, the output is 1. Otherwise, the output is 0. Now, so this is what we really want to do. In order to find the perceptron, what we really want to do is to find the equation for this hyperplane such that all the positive red dots lie on one side and all of these blue dots from the negative class lie on the other side. But before we continue, let's look at how the classification rule itself works. Ignore the text on the screen for now. This is, let me explain it with a figure instead. Let me get a new section here. Now, when I have an equation of this kind, summation I wi xi equals 0. This is the equation for the hyperplane that separates the positive and the negative class, right? I'm not sure how I got this done. Now, I can take all of these wi guys and write them into a vector. Let me call this w. I can take all of these x's and also write them into a vector, xn minus 1. And so this equation is the same as saying w transpose x equals 0. What does this mean? What does this tell you about the relationship between w and x? Anyone?
They are orthogonal.
They are orthogonal, right? So this equation, which is the same as this equation, is represents the set of all x's that are orthogonal to W. So if I have my x1, suppose it's two-dimensional and I have an x1, x2 plane, if I have some W of this kind, which is my W, the set of x's that satisfy this equation is going to be the set of x's that is at 90 degrees to W. So the this is the set of all x's that are at normal to W. W is normal to the hyperplane that separates the two classes. But then there is something more. This is an inner product. So let's consider some x which is not on the plane. So let's consider, say, an x out here. Okay. What is the value of W transpose X going to be for X over here? Is it going to be positive or is it going to be negative?
It'll be positive.
It's going to be positive because W transpose X, as we know, is simply mod W mod X cos theta, right? And here, this theta is less than 90 degrees. So when X points in the same direction or as W with respect to this plane, the product is going to be, the inner product is going to be positive. Suppose I have an X out here on the other side. What will the inner product be?
Negative.
It's going to be negative because now you have this angle theta, right? And so the inner product cos theta for theta greater than 90 degrees is negative. And cos theta for theta less than 90 degrees is going to be positive, right? So, and this is independent of, this is independent of the sign. And so for all x's on this side of the plane, W transpose X is going to be positive. For all x's on this side of the plane, W transpose X is going to be negative. Did that make sense to everybody? If it didn't make sense, raise your hands. No, everybody got it, okay? And so this really means that we want to find the weight vector such that W transpose X is positive. Oh my God, there's some bugs with the slide. Red is 1, blue is positive and negative class. So this should be pointing. The text is wrong, I'll fix this. But you want to find a weight vector such that W transpose X is positive for all of these red guys and it's negative for all of these blue guys. Make sense? If that didn't make sense, raise your hands. So now let me, yes, Amy?
So on this hyperplane, I had a question.
Yeah.
So for instance, let's say this hyperplane starts out with like misclassifying some of the red dots and the blue dots. Like when you're iterating, how do you know?
So we haven't even got into iteration, right? I'm telling you what we want to find. We want to find a hyperplane such that the inner product between the axis and the weight vector is positive for these guys and negative for these guys.
Okay.
Right?
I just wanted to, okay, it's fine.
Okay, just, bear with me for a few minutes, okay?
All right.
So this makes sense to everybody, I assume. Now, let me ask you this question. I have this, my drawing skills are really bad, but let's say I have this vector X over here, and this belongs to my positive class. Then what is the ideal? I want to find the plane that puts this on the correct side of the plane, on the appropriate side of the plane, right? What is the ideal, the best direction for the weights vector? Anybody want to tell me?
X1 plus X2.
So Aditya, can you, you're faint, can you increase your volume?
X1 plus X2.
There is no X2, right? I mean, not X1 plus X2.
Yeah.
No, I mean, yeah. So I'm saying this vector X, X1 and X2 are the axes. So,
Oh yeah. Right.
Anybody else?
If the weight points exactly to that direction, I think that would be
Exactly. You want the weight to be pointing exactly in this direction. You want the weight to be this, right? That's when you're going to get the boundary like so, and theta is 0. You want x to align with the weights. That's when you have the best case for x being on the correct side of the plane. Make sense to everyone? So you want w equals x. Now suppose I have another x, and this belongs to, say, the negative class. So this is some other x, and this belongs to the -1 class. Then where do you want the weight vector to be?
On the line that makes between x green and x red.
No, ignore the red. There is no red. I've given you only one. Yeah.
The positive, negative, the weight will be the line that's from those two vectors.
So no, this is x1, this is x2. This is a new plot. I've given you a new x which belongs to the class -1. What is the ideal weight?
You want it to be in the opposite direction of the green.
You actually want this to be the weight, the exact opposite, right? That way, you're going to get this side as the positive class, and this is most strongly guaranteed. How did that disappear? Something happened, right? But, okay, this is x. So this is most strongly guaranteed to be in the negative class. So when x is +1, x belongs to the +1 class, your ideal weight is x. When x belongs to the -1 class, your ideal weight is -x. Did that make sense to everyone? Anybody who didn't get that? So if you didn't get it, raise your hands, because I'm just going to continue in a few seconds. Okay. So assuming you got that, that completely explains the perceptron algorithm. It's an iterative algorithm. I'm going to start off with some initial guess for my boundary, but the boundary is defined entirely by the weights vector, as we saw, because the weights vector specifies the hyperplane that's orthogonal to it, normal to it, and then you begin testing each of your training instances. If the instance is in the positive class, but it has been misclassified as being in the negative class, then you're going to pull the weights vector towards the ideal weights vector for that instance. You remember, for any positive instance, the ideal weights vector is x itself. So you're going to try to pull w towards x, and you will do so by adding x to it. On the other hand, if you have an instance from the negative class that is misclassified as positive, then the ideal weights vector for that instance is going to be exactly opposite to that instance. It is -x, and so you're going to try to push the weights vector towards the ideal weights vector for this negative instance. So you're going to update your weight as w minus x. Let's try to, and I can, yeah, Chris?
First, please repeat that.
Okay, so I have some, actually, let me try to do this with the figure again. Let me draw a new figure. Let me delete that. So here's what is going to happen. I started off with some initial weights vector, right? This is my weights vector, W. And so this side is the +1 side now, according to this weights vector. This side is the -1 side. And now I got this one instance, which is out here, and this belongs to the class +1. If this belongs to the class +1, this is being misclassified, right? Now, what is the ideal weights vector for this guy? Chris?
It's x itself.
You're very faint, but the ideal weights vector is going to point directly at this guy, correct?
Yes.
So I'm going to try to drag this fellow out here.
Right.
And I will do this by adding x to this guy.
Okay, makes sense.
Right? And so now, similarly, suppose I have an initial weights vector, which say calls this guy +1 and calls this guy -1. And I have some instance out here, which belongs to the -1 class. And it just happened to fall in the +1 region. What is the ideal weights vector for this guy?
It's -x itself.
It's going to be this one, correct?
Yes.
And this was the weights vector. So I'm going to try to drag this guy out here. And so I will do so by subtracting x. Make sense to everyone?
Yep.
Yeah. That's a trivial algorithm, and the intuition is very clear. I can write some ugly math for it. I'll skip the math, I'll skip the explanation, but here is how pictorially you can see what happens. I have all of these red and blue dots, and I randomly initialize my weights vector, and I'm going to get some decision boundary of this kind. And now I begin checking every training point. I find, this is my initialization, I find this negative instance is misclassified. So I'm going to try to push the weights vector to point directly opposite, away from the negative instance. So I'm going to subtract that negative instance from W, which will give me this new weights vector, and I have a new decision boundary, and voila, that negative instance got properly classified. But then I continue checking my data points. I find this guy is a positive instance that's misclassified. And so I'm going to try to drag the weights vector towards that positive instance. So I add it to the weights vector, which gives me a new weights vector, shifts the boundary, perfect classification, no more updates, we're done. Everybody get that? Okay. And so this is the perceptron algorithm, very simple, very trivial, and it has this guarantee that if your data points can be separated using a hyperplane, then you will find it in a finite number of steps. It's a computationally feasible algorithm. The details for how many steps you will take are on the slides. I'm going to skip it. For our purpose, this is all we really need to know.
Professor, we have a poll now.
Go ahead. So Chris, what's your question while they're calling up the poll?
Right. So on the being linearly separable, how do you know when to stop? You know, because there might be cases of error that you can't deal with.
So if the classes are linearly separable, then you have a theoretical guarantee that there is no error that you can deal with.
Right. Okay. The poll is gone. Jeez. Uh-oh.
Yeah. Okay, we're done with the poll. I'll stop this, right? Yeah, it's true. Clearly, we just stated it. Now let's look at a more complicated problem. So I assume everybody got what we were discussing so far. I'm going slower than I intended to, but it's important that you get these ideas. Now, say I want to learn an MLP for this function. I want to learn an MLP which produces a 1 for inputs inside this double pentagon and 0 outside. And we know that this decision boundaries can be perfectly modeled using an MLP of this structure. We've seen this in the last class and the class before that. And so, but then we're going to only have these training data points. We will not have the boundaries themselves. And so the question is, using only these data points, the red and the blue points, where the red points are labeled 1 and the blue points are labeled 0, can we use the perceptron algorithm to learn the parameters of this perfectly structured network? The structure is just right. All we have to learn are the weights and the biases such that this guy actually captures this decision boundary. Can we learn it using the perceptron algorithm? And again, remember, the perceptron algorithm just keeps making incremental corrections to the weights whenever it encounters an error. Now, the in order to do this, every single perceptron over here must learn the correct decision boundary for itself. So for example, these 5 perceptrons must each learn these 5 purple lines. These 5 perceptrons must learn each of these 5 gray lines, and this perceptron must learn to fire when either of these 2 guys have fired. This is what, and that is also a linear decision boundary. And each of these perceptrons must learn their decision boundaries for the entire network to be learned. Now, for simplicity, let's assume that all of these 4 perceptrons and all of these guys, they have already learned their decision boundaries. Just assume so, okay? So now this is the only perceptron that remains to be learned. Now, this one perceptron must learn this boundary, right, in order to complete the pattern. Now, the training data labels that we have are like so, with the reds and with the points inside the double pentagon labeled 1, which are the reds, and the points outside the double pentagon labeled 0, which are the blues. Can the perceptron learning rule learn this line from these points? Anyone?
No.
Why not?
Because it'll see the blue dots on the positive side and it'll adjust the weights again.
So because the classes are not linearly separable, the perceptron learning rule cannot learn this boundary, right? So in order to make it learn the boundary, what must we do?
Reclassify.
We want to relabel all of this. Is the kind of data that we want in order to be able to learn the boundary for that last guy. Correct? And so what we need to do is to relabel all of those yellow starred dots from blue to red, just so that you can learn this one boundary.
Could we also kernelize?
Pardon me, I couldn't understand that.
I believe it was called kernelizing, where you add a dimension to the data.
Oh yeah, sure, but it doesn't matter. That's irrelevant, right? The point, the real key point over here is that all of these blue dots must be recolored red in order to be able to learn this boundary and complete the patterns. That makes sense, right?
Yes.
Okay. What's the problem with doing so? Take a look at this figure.
Has to be done manually?
Well, you're not going to be able to do it manually because here I'm giving you a visual pattern. I gave you the answer. Now, in reality, you don't have the answer. You don't know that you're looking for a double pentagon, even in 2 dimensions. So the only way you can do this, right, is to check every possible way of relabeling all the blue dots. This is assuming all of these other perceptrons have already captured their boundaries, right? So you're going to relabel each of these blue dots and a different subset of these blue dots and learn a decision boundary for this guy. Then you plug the decision boundary into the entire network and see if the final network is correctly classifying the red and the blue dots. If it's not doing so, then you must try a different relabeling. And keep doing this till you find a relabeling, which is this one, such that when you learn a decision boundary using this relabeling, you will get this line, and this will complete the pattern. Does that make sense? If it didn't make sense, raise your hands.
So are we saying that all of those blue dots should be classified as red and dot, like be tried
only by this guy? Say only by this guy, right? Each of these guys is going to need a different relabeling.
Oh wow.
Right? Because this guy has to put a 1 on this side in order to compose this pentagon, correct?
Yes.
right? So here is the point. We are going to have to try out every possible way of relabeling all of the blue dots just to learn the one line for this one perceptron. And the fact is, we're going to have to do this for every single perceptron in the network. There was a question. What was that?
So in general, when we have more data points in our data set, that's supposed to be a good thing for our algorithm, right? But here, when we have more points, there are going to be exponentially many.
Thank you. Yes. So I want you to get rid of every single notion you ever have learned in your life when you go through this class.
Okay.
Because you're going to continuously run into contradictions. So there is no religion over here. It's all rational logic, right?
Okay.
And if I'm trying to use something like the perceptron rule to learn the classifier, in order to learn every one of these neurons, I'm going to require an exponential search over all of the training data points. So the overall search, where I relabel all of the data points and try to find the perceptron, and then compose all of the perceptrons and determine if this is actually giving me a correct classification, that's going to be exponential, at least exponential, in both the number of inputs and the number of perceptrons. So here is the situation. If we had tried to learn this entire network, we're learning the perceptron algorithm. Even if the network has the perfect architecture, we need to know the desired output for every one of these perceptrons, which means you need to know the correct relabeling for every one of these perceptrons, and the relabeling is perceptron specific. And so the whole thing is now going to be simply a, yes, Yara? Go ahead, Ira. What was the question? Was there a question?
Professor, I don't quite understand why it's exponential. Can you explain it in a bit more?
Okay, so think about it this way, right? Here, I have to relabel every point. So what are basically, if I'm relabeling every point, what I'm doing, let me get rid of all of the dots here, this ugly figure. If I'm relabeling every point, let's say these are my points, I'm going to call them x1, x2, x3, x4, xn. So first, I got some labels, 1, 0s, 1, 0, 0, 1. This I have already been given. I'm ignoring this. I'm going to start off by calling this 1, 0, 0, 0, 0. I will try this guy. Then I'm going to try this, 0, 1, 0, 0, 0. And I'll keep doing this. Then next I'm going to try 1, 1, 0, 0, 0. 1, 0, 1, 0, 0, right? And I'm going to try the entire combination of 2. Then I'm going to try 1, 1, 1, 0, 0, 0. How many such combinations exist? If you have n inputs, each input can take 2 values, 1 or 0. So you have 2 raised to n such combinations, correct?
Yeah, gotcha. Thank you for this.
So it's exponential for each neuron, and then you have a large number of neurons. You have to see how the neurons combine with one another, so it's also exponential in the number of neurons. And then you have the other issue that for each of these, the perceptron algorithm itself might take its own time. So the entire computation is at least exponential in both the number of inputs and the number of neurons. It's not the dimensionality of the input, it's the number of inputs. Everybody get that? Any questions? So this...
Professor, we have a poll.
Yeah, go ahead. Okay, I'll stop this in 5 seconds. So hurry up. All right. Let's stop this. Thank you. Anyway, so the fourth one was correct, right? There are many conditions you have to satisfy. You need to have, it's an exponential time, so you need infinite compute resources. And the classes must be separable. We're not speaking of linearly separable, but you should be able to find boundaries that clearly separate the classes. Otherwise, the whole thing won't work. The perceptron algorithm itself won't work. And on top of that, the network that you have should be capable of capturing these boundaries. Otherwise, the whole thing won't work. And so the perceptron algorithm cannot be directly used to learn an NLP because of the exponential complexity problem. We can try to use greedy algorithms instead. And so Bernie Widrow back in the day came up with these beautiful algorithms called Adeline and Madeline, which are greedy algorithms to try to solve this problem. They're still very valid. They are explained in some detail on the slides. They will figure in the quiz. Please take a look. And so here's the story so far. Learning a network is the same as learning the weights and biases to compute a target function. In practice, we learn networks by fitting them to match the input-output relationship of training instances drawn from the target function. A linear boundary can be learned by a single perceptron. Non-linear boundaries will require networks of perceptrons. All of this is from the previous lectures. What we learned today was training an NLP with threshold functions as activations will require knowledge of the input-output relationship for every training instance for every perceptron in the network. And this is a combinatorial optimization problem, or maybe NP complete. So, which is why, when people realized that training an entire NLP was a combinatorial optimization problem, all progress, all research in this field stopped for well over a decade while people were trying to figure out how to deal with this. Till we had this really nice paper by this guy in MIT on backpropagation, which, how do I forget his name? I don't remember. Anyways, so to understand why this is the case, let's go back and see why we have this problem. In fact, let's ignore this figure and let me draw the figure myself. So suppose I have all of these pluses and all of these minuses, right? I know that I can draw this. I can draw a classification boundary, which will separate the two. No big deal, right? Let me also draw the axes. These are my axes. But now, suppose I have a. Let me add a minus here. This will convenient. Suppose I have this minus. Now, suppose my initial guess for the decision boundary was this guy, which calls this plus and this minus, okay? Then it's making an error, correct? It's misclassifying this point. Now, what is the obvious thing to do when you find that this decision boundary, which has this weight, is misclassifying a point? You're going to wiggle it, right? So you start off by wiggling it. You say, I'm going to move it this way, and you move it to this one. When you did that decrease the total error? Anyone? Did that decrease the total error?
Yes, yeah.
Did it?
No.
No.
There's still
right. So what if I wiggle it to this point? I rotated it the other way. Did that decrease the total error?
No.
No, right? Which of these two is a direction I must continue in?
Going to the top.
Clockwise.
The clockwise, the first one, correct? But then if I'm simply counting the errors, based on counting the errors, I will not be able to decide just by wiggling it and testing both directions, which one is the correct direction to continue. You see the point? Because if I'm counting errors, I moved it a little counterclockwise, I counted the errors, I have an error. I move it a little clockwise, I count the errors, I still have the same number of errors. So just by counting the errors, I cannot tell you whether I'm doing the right thing and whether I should continue doing this or whether I should go the other way. Does that make sense?
So you need to know like how big those errors are, I'm guessing.
You need to know how far away you are. And if you don't know this, then you won't know which direction to go in. Right? And what is the problem with the threshold activation function? When I slide it, if I rotate this, remember, this guy is a heavy side function, correct? So if I take this step function and I rotate it, it's still only just counting errors. The step function by itself doesn't tell me how far I am from the boundary, if I'm just looking at the value of the function itself. Make sense to you guys?
Yeah.
So what we really need, and if I go up to an even higher, more complex problem like this guy, it gets much worse because there are so many perceptrons and I can sort of wiggle all of their boundaries, and wiggling their boundaries doesn't tell me if the error is, if I'm doing the correct thing or not, because for small wiggles, the error is not going to go down or up. It's going to stay mostly the same. Just by looking at, the direction in which I wiggled and counting the errors, I will not know whether I should continue doing what I'm doing or whether I should do something else. Does that make sense to everybody? Questions? So here's what we're going to do. There's a second problem. In real life, your data are not really going to be separable. So the whole perceptron theory is also going to fall a bit on its face. And but even assuming that the data are separable, which is what I'm going to continue doing, because it gets the idea, you have this problem. So what we will do is we are going to make the neuron differentiable with non-zero derivatives over the input space. What does this mean? So if you count the errors over here, we're going to do two things. This is kind of, we're going to ignore what's on the slides for now, right? Let me start off. We were committing two mistakes over here. What was the first mistake? Anybody? I mean, not a mistake, but what was the first problem? Somebody mentioned it. Pardon me?
We cannot tell the distance of the force.
Exactly. So we cannot tell the distance of the point to the boundary. Correct. So this means that counting errors, which is, we are trying to minimize the total count of errors, but for whatever reason, counting errors, which is the actual objective we want to minimize, is not the correct thing to be wiggling this guy, right? What we really want is the distance. Now remember that minimizing the distance is not the same as minimizing the errors. But if we had a notion of the distance now, the problem with trying to compute the distance is, again, you're going to have to find this boundary, you're going to have to compute the distance. You need a way of computing that. So a different way of saying this is that if you look at our objective function, which is the total error, that the derivative of that objective function with respect to the angle of this line is 0. If you just wiggle this, small perturbations in the angle of the line do not change the count. So the function, the step function, has this horrible property that the derivative is 0 everywhere except at this boundary where it's not defined. So what we will do instead, and which is what gives us the problem that we don't know which way to move in. So this figure explains it. I have all of these blue dots, I have these red dots. They are perfectly separable by a threshold activation or by a classifier. But if my initial guess for the perceptron is this dotted line, then if the parameter of the perceptron is this threshold, if I wiggle this dotted line back and forth, the total count of errors is going to remain the same in both cases. So the count of errors will not tell me if I'm doing the right thing in moving the perceptron back and forth, the threshold back and forth. But now let me change the activation function. Instead of changing this, using this threshold activation, let me use the smoother version, which is the sigmoid. The criterion I'm going to use for actual classification is to say that if the value of the function is greater than 0.5, I'm going to call it class 1. If it's less than 0.5, I'm going to call it class 0. When I do that, in this case, how many instances are being misclassified? Anyone? On the left-hand side?
1.
This one guy is being misclassified, right? But then there's something else I can do. I can compute the distance from this point to the curve. Here, the distances are either 1 or 0. That is the problem from the function, right? I would explicitly have to compute the boundary, and in a multi-layer perceptron, those boundaries can be immensely complex. For a single perceptron, maybe not. For a multi-layer perceptron, the boundaries are going to be immensely complex. So you can't begin finding the boundaries and finding how far you are from the boundary. You're much better off if you simply compute the value from the, if you're able to compute the distance from the function. So it's much better if you're able to compute, it's much easier to compute the distance from this dotted curve than from this threshold. And that over here doesn't change when you move the threshold left or right. Here, if I compute the distance from the red line, from the dots to this curve, that's 0 for most of these guys. It's somewhat large for this one. It's somewhat lesser for this one. It's almost 0 for these guys. But then if I move this curve left, as I did out here, what you find is that the total distance over here actually went down. How many errors am I making on the right-hand side? Anyone?
1.
I'm still making the same number of errors, right? But yet, I already have an indication that moving the curve left is a good thing to do, right? Because the total length of these dotted lines decreased. If that didn't make sense, raise your hands. Seems to have made sense. So instead of counting errors, if I computed the total length of these dotted lines, and I adjusted this function to minimize the total length of those dotted lines, then that will give me an indication of which way to move the threshold, which way to move the parameters. Make sense to everybody? So if it didn't, raise your hands. What's the problem with this guy? What we really want to do is to minimize the total count of errors. What we are actually minimizing is the total length of these lines. We are hoping, yes, Ran?
I just got a question. What if there are a lot of blue dots which is very close to the left-right nodes? Then the total length will be increased also.
Thank you. Right? So what happens? We are using this total length to decide which way to move the curve, but there's no guarantee that minimizing this total length is actually going to minimize the error for the reason that Ran just suggested. See what I'm getting at? For example, here, the total length is lesser on the right, but the number of errors is the same, right? Now I can have some things which are, if I begin adding all of these lines over here for each of these dots, then I could have a large number of points out here which contribute so much to the length or I could have a large number of points out here which contribute so much to the length that they sort of pull the curve right or pull the curve left and sort of disproportionately affect the curve and make it move in the wrong direction. You're going to become dependent on how many training instances you have, how they are laid out, etc. It's a trade-off. You have this new function which doesn't actually count error. It gives you it's something else which you think is related to error. And if you minimize that, you're hoping the error will go down. That's what we're going to do, right? And to do that, you need these functions which continuously vary, because if you have a function like the threshold, that the total distance is just going to be the total error count. And so what kind of function that makes most sense for us? This particular one, which is the sigmoid, has a very nice interpretation. We saw this, I think, in the last class. This sigmoid can be interpreted as the posterior probability of the class being 1 given x. It's given by this formula here. You can see how this formula works. If z is a large negative number, e raised to minus z becomes a large positive number, so this becomes 0. So out in minus infinity, this becomes 0. If z is a large positive number, this becomes e raised to minus z becomes 0. So sigma becomes 1. So out here it's 1, and in between it smoothly varies. This whole thing can be viewed as a computing the a posteriori probability of y being 1 given x. We'll spend more time on that in a later lecture. But for now, we will return to the fact that perceptrons with sigmoidal activations actually model class probabilities. Well, we'll get back to this issue later. But for now, let's look at something else. Because this perceptron activation is differentiable, something interesting happens. We can now compute the derivative. This is differentiable, right? So again, you can compute the derivative of y with respect to z, dy over dz, which is sigma prime of z. And this z is an affine combination of the inputs. And so you can compute the derivative of z with respect to each of these weights, and also with respect to each of the inputs, which means that using the chain rule, you can compute the derivative of the output with respect to each of these weights. It's simply dy over dz times dz over dwi, which is sigma prime z times xi. Or you can even compute the derivative of y with respect to the inputs. Dy over dx is dy over dz times dz over dx, which is sigma prime z times wi. The point of all of this is that now this output is differentiable with respect to all of these guys. Now, what does it mean for something to be differentiable? It means that you can now say how much a small perturbation of this value will change this guy. That is the notion of differentiability, right? If I compute the derivative of y with respect to some term, it tells me if I change this term by a very small amount, how much is y going to change? And so this in turn means that I can tell you how much the output will change and how it will change for small perturbations of the input, not just for individual neurons, but because these are networked for every single parameter in the network. So for instance, all of these neurons are now have differentiable activations, which means I can tell you how much a small perturbation of the weight for this edge will affect the output of this neuron. I can tell you how much a small perturbation of the output of this neuron is going to affect the output of this guy, how much it's going to affect the output of this guy. And so I can also tell you how much small perturbations of these fellows are going to affect y. And so when I sort of chain it all up, I can tell you how much a small perturbation of this weight is going to affect the final output of the network. And it's not only going to tell you how much, but how. And so I will be able to tell you that if I increase this w by a little bit, y decreases at that particular x. And then if I can compute that value, then I know how much the distance between the target y and this actual output of the network changes. And now I can use that to adjust my w. That's how differentiability affects the entire computation. Did that make sense to you guys? Questions? If that didn't make sense, raise your hands, because we're going to be building off this. Okay, I'm assuming you got it. So this means this overall function is differentiable, and it's differentiable with respect to every parameter in the network. We can compute how small changes in every parameter change the output. And we can also, and this we can actually use these derivatives in a chain rule to actually figure out how to adjust the parameters of the network to improve the the manner in which the network is modeling the function. So here is the overall setting now for learning an MLP. You will be given a collection of input-output pairs. These are your samples, where D is the desired output, X is the corresponding input. Both may be vectors, and we want to find the network parameters such that the network computes the desired output for each training input, or a close approximation to it. The architecture is going to be specified for us. Now, remember here's what we actually did. We originally, so this was our problem, right? We had some function that we wanted to model. The network actually computes some other value, and we wanted to minimize this error, which is basically the integral of the divergence between, where the divergence quantifies the difference between the actual and the desired outputs. And we minimized the integral of this divergence. We would like to minimize the integral of this divergence over all of the inputs. Now, one of the things that happens is that the network is a perfect approximate. It's an approximator, but it's not guaranteed to give you a perfect replica of the function that you want. So, given that, instead of simply just trying to minimize this area everywhere, suppose you were informed that in reality these inputs will never be seen, then it's better for you to just focus on the area over here and try to minimize it, and not try to do anything out in these regions, because those inputs are never going to be seen. And that way you can do a better job of approximating the function in this region at the cost of the other values of X, which will never, at the cost of the approximation in regions of the input, which will never be seen. So what we really want to do is to have this weighted weighted integral. Instead of simply minimizing the this divergence, you're going to weight the divergence at each point by the likelihood that that particular input will be seen. So this is the actual divergence that we are going to try to minimize, which is the divergence. This is the actual function we're going to try to minimize. It's the divergence between the actual output of the network and the desired output of the network, weighted by the probability of that particular input, integrated over the entire input. This, of course, is simply the expected value of the divergence. And so what we really want to do is to find the weights that minimize this expected value of the divergence between the actual output of the network and the desired output of the network. This is what we want to do. And
Professor,
again,
we have a poll.
Yeah. Okay, so again, we have the situation that we don't actually have g of x defined everywhere. we are only going to have the value of g of x at some specific points. And so what we will do is to sample the points, but so long as you sample from the natural distribution of the data, you will naturally be assigning more importance to points which are more probable than to points that are less probable. And so what we will actually do is this. Instead of trying to minimize this entire area, we are going to define the divergence at every one of these points. So these are all the samples that we took. And we are going to compute the divergence between the actual output of the network and the desired output of the network at every one of these points, which is all of these lines. And you're going to compute the average length of these lines. And you're going to use the average length of these lines as a proxy for this area. And what we will actually minimize is this average length of the line, because this is something we can compute, whereas this upper term, which is the expected divergence, is something that we cannot compute. This average, the average length of the line, the average divergence, is what we will call the empirical risk. So this term over here, the expected divergence, is what we call the risk. We would like to minimize the risk. We would like to find the parameters W that minimize the risk. In practice, you cannot compute the risk. You're going to get an empirical or the expected risk. So we're going to compute an empirical estimate of the expected risk, which is the average divergence. This is your empirical risk. And so our actual, objective that we will minimize is going to be the empirical risk. Now, and what we will perform is empirical risk minimization. Now, bear with me for a couple of minutes more. Why is this a good thing to do? Now, observe that if I go back to this function here, minimizing the error at each of these points doesn't necessarily guarantee that it's minimizing these areas. You might just be locally minimizing stuff out here and not be minimizing things anywhere else. So why is this? Why do we even do this? Now, here's what we have. We have the empirical risk is 1 over n summation over, these are all of my training points. This is the divergence for xi, right? And so if I take the expected value of this empirical risk, this is going to be 1 over n summation I, expected value of the divergence of xi. This guy is the actual risk. This is the expected divergence. So this is going to be 1 over n times summation I, my actual risk, which is simply going to be 1 over n times nr. Strike all the n's. This is r. So this means that the expected value of my empirical risk is the true risk. So the empirical risk over here is an unbiased estimator of this guy. What that means is that if I ran this experiment millions of times, where in each experiment I pulled out and sampled my data n times and computed the average divergence, then the average divergence, the average of all of these average divergences would be this guy. So basically what we are saying is that this empirical risk is an unbiased estimator of the true risk. And so we hope, again, this is hope, that if you minimize the empirical risk, you will also minimize the true risk. And so that is why what we will do is perform as empirical risk minimization, where we compute a bunch of training points, we draw a bunch of training points, we compute the average divergence of all of these training points, and we estimate the weights to minimize this average divergence. Yes, Shams?
I think I didn't understand what we meant by natural distribution of x's, px.
So what I mean by natural distribution of x's is, let's say I have some x, and I say, in reality, I only see data from this region. I never see data from here, right? How frequently do you see cats with 7 heads? You just don't see them. So you're not going to imagine every possible distribution of cats. You're going to focus on cats with 1 head, for instance. So these things have a natural distribution. If you're trying to model cats, you're not going to focus any time on modeling distorted cats.
Yeah, but like if we were trying to approximate a target function, then
so if your x has a distribution of this kind, p of x, and this is x, then you want to take more samples from this region and fewer samples from here, and no samples from improbable regions.
Oh, thank you.
Right? That's what I mean. And what happens is if you just naturally sample data in real life, that's exactly what you're going to get. You're going to get draws from the natural distribution of the data.
Thank you.
And so, again, terminology. This is, I've got 2 more slides, so just bear with me. Although I'm calling the empirical risk, the standard terminology is to call this a loss. This empirical risk or the loss is only an empirical approximation to the true risk, which is the expected divergence between the target and desired function. And this guy, if I give you the training data, I've given you the x's, I've given you the desired value for the function at x. The only thing that you're allowed to change now is the weight. So for a given training data set, the only variable that remains here is the weight. So this empirical risk or the loss is a function of only the weights. And so here is our problem statement. You're given a collection of training inputs, training samples, which are input-output pairs. We will define the average divergence, which is over the training instances, which is what we call our loss. This loss is our best estimate for the actual risk, the actual error that our network is making. And we are trying to minimize this loss with respect to the parameters of the network. So you have defined a function, which is a function of the network parameters, and we are going to try to minimize this function with respect to the network parameters. So this is a problem of function minimization. It's an instance of optimization. And so here is the story for today. We learn networks by fitting them to training instances drawn from a target function. Learning these networks using threshold activation perceptrons requires solving hard combinatorial optimization problems. So instead, we will use continuous activation functions with non-zero derivatives which can enable us to estimate network parameters. Now here is this thing, a differentiable divergence between the output of the network and the desired output of the training instances. You want this, you want to be able to determine how much a small change of the parameters changes this length. So the manner in which you compute this length must also be differentiable. The divergence function itself must be differentiable. And then we optimize the network parameters to minimize this average divergence, which is basically our proxy for the real error. And this is a function of instance of function minimization. I'll stop here. If you have any questions, I can take them. Any questions? Yes, Alex?
Oh, can we see the note that you went through the mathematics on why empirical risk is an unbiased estimator for time risk? Yeah, that one. Thanks.
Yeah. So this is my risk, right? So this is how I define my risk. If I take the expectation on both sides, because this is linear, the expectation went inside. This is just the expectation of a divergence. That is the risk, right? So replacing this risk value in this equation, it's 1 over n times summation I equals 1 to n r. R is a fixed value. It's the risk, actual risk. So that's just this summation is simply going to give you n times r. There's a division by n. These cancel out. You end up left with r.
Okay, thanks. That makes it much clearer. Thank you.
Right. Anything else? Yes, Hadan?
Hi, I have a question about perception algorithm.
Uh-huh.
So when we had a misclassified sample, we just simply calculate the error and add it to the weight.
Yeah.
And you mentioned that this problem, sometimes we don't know like how far the misclassified sample is, or we don't know the error. So that's why it's not very useful when we try to adjust the weight. But I feel like we can just calculate the distance, right, in this case.
So here is the point, right? For the simple linear boundary, the perceptron algorithm itself works, not a problem, right? For this guy, you don't act. Now, I'm giving you a trivial example, even in two-dimensional space, right? I give you 10 first level, I give you 10 first level perceptrons, okay? And then I give you a point over here. Let's say this guy. Let's say this point has been misclassified. How do you find the boundary to decide how far it is from the boundary? There are many, you don't know the boundary beforehand, right? You have to check it against all of these lines. How many of them will you get? Even for this trivial problem. Because you don't know a priori which boundary it is, what the boundary is. So which is the boundary that is actually closest to the current point? That is not possible to compute, even for something as trivial as this, just by looking at the functions.
I see. And
Right?
I think only when it comes to like we have one misclassified point and all other points are classified correctly, we can use the
Even then
perceptron
it's hard, because if I just gave you this one misclassified point, right, I'm going to have to check against 2 raised to 10 possible boundaries.
Oh, I see. Okay.
Right? It's just not possible.
I see. That's much clearer now. Thank you.
Yeah. Any other questions, guys?